Hello class. In this video we're going to be looking at the derivative and integral rules of inverse trig functions. So this is something that's, at least at A&T, we leave this out of Calculus 1, and it's mainly just because we don't really need a lot of the patterns we get here until Calculus 2. Really, I mean, we could do so, but let's start with a little bit of a reminder of how our inverse trig functions work. So if you remember that, say, sine, typically we give sine an angle, okay, and it gives us a ratio. All right, in this case, typically we call our angle theta, let's say, and sine gives us, if theta is sitting in a right triangle, it gives us the side opposite over the hypotenuse. Okay, so in this case, sine of theta would be opposite over hypotenuse. Okay, so that's our ratio. So we give sine an angle, it gives us some ratio of a triangle. Okay, the inverse trig functions just work the opposite way. Sine inverse, we give it a ratio, okay, and it tells us what angle would be required to get that ratio. So we might give it, in this case, we would give sine inverse some ratio opposite over hypotenuse, and it would give us the angle theta. Okay, so it just kind of works opposite. And this could also sit on a circle, right? X, Y coordinates, and that's how every trig function basically works. Trig functions, you give them an angle and it tells you a ratio of some kind based on a right triangle or the unit circle. And the inverse function, we give it the ratio we want and it tells us, it spits out the angle needed to do that. Now there's some things to keep in mind here as far as restrictions on the inverse function. So for some of our restrictions, so this sine inverse, of course, we give it a ratio, it gives us a theta, but that theta can only be between 0, sorry, that's not right, thinking of cosine. Okay, it can only be between negative pi over 2 and pi over 2. Okay, and the same for tan inverse. If we give it a ratio, it'll give us a theta, but that theta is only between negative pi over 2 and pi over 2. Okay. Cosine is the one that's different. Cosine inverse, we give it a ratio, it gives us an angle, but that angle is between 0 and pi. Okay, so in other words, the inverse sine and inverse tangent basically only gives us angles here from negative pi over 2 to pi over 2, while cosine inverse only gives us these top half angles from 0 to pi. It is just this idea, we give it a ratio, it gives us an angle, but it is definitely restricted. It's tricky. Okay, so we are going to start trying to find the calculus rules for our inverse trig functions. And we're going to do it in much the same way we found rules for like natural log and things back in Calculus 1. We're going to use implicit differentiation or just a general chain rule. Okay, so it's probably been a while since you've seen implicit differentiation. But hopefully not a while since you've seen the chain rule. Okay, so we're just basically going to be using a chain rule. So here's how we'll start. We'll start with just y equals sine inverse of x. And we want to find the derivative, dy dx. Okay? Now, as given, we can't really do that because we don't know the rule for sine inverse. So what we're going to do is instead we'll take sine of both sides. And you'll see why we do this in just a second. So we'll get sine of y. And then here we'll get sine of sine inverse of x. So we do that because the nice thing about inverse functions is if you plug an inverse function into its inverse, so sine of sine inverse, they cancel. So we get sine of y is equal to x. Okay, and it cancels out nicely like that. All right, so now what we have here, we have this set up now in a way we can use it. We know the derivative of sine, we know the derivative of x, so now we can just take the derivative of both sides. Okay, and the derivative of sine, of course, is cosine, but here it's cosine of the stuff. Since we have sine of some stuff, now it's going to be cosine of the stuff, then times the derivative of the stuff. Okay, dy dx. And then that will be equal to, and that's just, this is our chain rule. And then here, the derivative of x, of course, is just 1. And so now we can solve for dy dx, which I'm sure you remember doing that in Cal 1. Of course, hopefully this one's a little nicer than the ones you may have seen in Cal 1. Okay, so we'll just divide over and we'll get that dy over dx is 1 over cosine y, also known as secant of y. Okay, we won't need that to continue this process, but you know. So now that we're here, okay, we need to get this. So this is a problem. I don't want the derivative of y in terms of y. We want this in terms of x. Okay, because I basically want a rule I can reference, right? So saying that the derivative, if I swing back up here, if I say, oh, okay, the derivative of sine y equals sine inverse. If I say the derivative of sine inverse is secant y, that doesn't mean anything really right now. So what we're going to do, it's called making a reference triangle. So we are going to make a reference triangle from this statement here. So we're going to create a reference triangle. So this is actually a trick we're going to be using a lot in this class. So it's actually good that we're kind of seeing this in a very first example today. Because we'll be using it a lot, especially in a few sections, but it could be a really helpful tool to completing these sine type problems. All right, so how do we do this? Well, remember, sine, we give it an angle. So here is the angle, which is y, and it spits out a ratio. So our ratio is x. Okay, so the angle is y and the ratio is x. So I'm going to draw myself a right triangle here. I'm going to put my angle, which is y. Okay, now we can fill out the rest of this triangle with our ratio. So a ratio, remember, sine of y, that's going to be Remember, sine is the side opposite over hypotenuse, right? Now, this doesn't look like a ratio. It just looks like a number, but remember, we can always sneak in a divided by 1 in here, right? So that's what we're going to do. We'll sneak in a divided by 1, math. So that means that x is going to be my side opposite, and 1 is going to be my hypotenuse. Okay, so I will put that over here. X is the side opposite, 1 is the hypotenuse, and now we just need to find the side adjacent. All right, so we do that with our Pythagorean theorem, right? The hypotenuse squared is equal to one side squared plus the other side squared. And you'll notice here that I'm just writing ADJ as just my adjacent side. Mainly because I like to just identify what it is I'm actually looking for, since we actually have some variables and stuff sneaking around in here. Usually we just have numbers in one variable, but we have two variables, and this just reminds me of what I'm trying to solve for. Okay, so we get 1 minus x squared is equal to adjacent squared. And so that tells us that plus or minus the square root of 1 minus x squared is equal to our side adjacent. Now the question becomes, which one of these do we choose, right? Do we choose the plus or the minus? And that actually comes from that thing I reminded us about before, what quadrant we have to be in. Since we're starting with sine inverse, right? Sine inverse, it spits out an angle that's between negative pi over 2 and pi over 2. Right, so on the unit circle, it's trapped in here. Right, so any triangle that we make here in these angles are going to look something like this. So all of them, the side adjacent, which I'll put in another color here, our side adjacent is positive. Okay, so that means we are going to choose the positive one. If that's, beyond your pay grade, that's fine. That's just why we're choosing this positive one. Okay, but that's where we use this restriction. So our side adjacent ends up just being the square root of 1 minus x squared. Okay, so now we can actually fill out what we have here or here. So cosine, remember, is adjacent over hypotenuse, and that makes secant hypotenuse over adjacent. Okay, so this is why we had to do this, because we needed this side adjacent to finish this off. So finally, we can, down here, let's do it. So dy over dx, which is secant y, which is hypotenuse over adjacent, which is 1 over the square root of 1 minus x squared. And there we go. There's our final derivative. We got it in terms of x like we wanted, and that's that. All right, now from here, we could go through this process multiple times. Using the same work, we can fill a lot of these out. I do want to focus a little bit on the secants, because there's some weird stuff going on there that we need to be good to talk about. But basically, we can follow the same exact process and get that cosine inverse is just negative 1 over the square root of 1 minus x squared. That comes from basically the fact that when we differentiate cosine of y at that step, we'll get negative sine y. And it just follows the same way. Following the same process, we can get the derivative of tan inverse is 1 over 1 plus x squared. And that cotangent inverse is negative 1 over 1 plus x squared. Notice this pattern here that once we know the, say, the normal one, the the co-function is literally just minus. Now, hopefully that somewhat makes sense based on what we know about the trig functions. I find these a little easier to memorize than the normal trig functions, just because I only need to know sine inverse, tangent inverse, and secant inverse when we get to it. And then the others are just negative of that. And because of that, actually, these don't crop up that much, especially with integrals. Now let's look at the secant one. Again, I don't want to do all the work all over again for every one of these, although it would be good practice if you wanted to see if you could get this, and get this, and get this. But there's some interesting... watch out whenever a math professor says interesting. But there's some interesting things that show up with the secant inverse, and it's one of those things that it's hard to remember, at least for me, it's hard to remember unless I know why it works the way that it does. So let's take a look at that one. We're going to go through the same process we did with finding the sine. Okay, so just like before, we're going to start with y equals secant inverse of x, and then take secant of both sides. Right? So we'll take secant of y is equal to secant of secant inverse of x. And just like before, we do that because this cancels. Okay, so we'll get secant y equals x. Now we'll differentiate both sides. I'll just put diff both sides. Here's where we use our chain rule. The derivative of secant of stuff is secant of the stuff times tangent of the stuff times the derivative of the stuff. So that's where our chain rule comes in. We don't need it here because the derivative of x with respect to x is just 1. So we're differentiating with respect to x. I guess I should write that there just to be clear. Okay? And now, just like before, we're going to divide this fella through and get that the derivative of y with respect to x is 1 over secant y tangent y. Now, we run into the same problem. I don't want y's in my final answer. That's not very useful. The secant y part, that's not bad. So let me identify this. This we could just replace right now with an x. So I could just say, oh, okay, well, the secant y becomes x, but we still have that tangent y that we need to deal with. Okay, and that's where our reference triangle is going to come in. So here we'll use a reference triangle. And we base it on this guy right here, what we started with. Let's give ourselves a little more room here. I'm going to draw a right triangle. Getting better at that, I think. And we're going to base it on secant. So remember here that the angle is y. So I'm going to put y in for the angle. And x here is the ratio. Now the ratio for secant, so remember, I'll write it over here, that secant is 1 over cosine. So it just flips cosine over. So if cosine is adjacent over hypotenuse, not meaning to write that sideways, but then secant just flips that over and it's hypotenuse over adjacent. And let me put some y's in here just so I'm writing some correct math. So the ratio is x, and remember we're going to throw in a over 1 there. X over 1, that makes x the hypotenuse and 1 the side adjacent. So 1 is the side adjacent, x is the hypotenuse, and now we need to find this side opposite. Okay, which again we do with our good friend the Pythagorean theorem. So x squared is going to be equal to 1 squared plus the side opposite squared. All right, so we'll move these things around. And now I get plus or minus the square root of x squared minus 1 is equal to the side opposite. The question here becomes, well, which one do we choose? Okay, I'm going to just put it in sort of as is, right? So there's a little bit of funky stuff going on up here. All right, let's just put this in as 1 over. I'm going to move the plus or minus outside. Plus or minus x square root of x squared minus 1. All right, now this little piece right here is always positive no matter what. That's why we have a plus or minus to make it plus or minus. And the question is, well, which one do we choose? And the answer to that depends on what's going on with x. Here's what we need to take into consideration. So I've prepared a graph of secant inverse here. So this is the graph of secant inverse. Okay, and as you can see, from the left to right, it is always increasing. Right, so here it increases up to here, and then there's nothing here between -1 and 1, and that's because, well, when we get back to it, I'll show you. And then it increases for the rest of its life. Okay, so that means since secant inverse always increases, the derivative must be positive. So you might think, oh, well, then we choose the positive. However, well, this is where we have to be careful. Notice that x can actually be negative. Okay? When x is negative, we're fine. Okay? And if x is positive, we're fine. The only thing we can't be is between -1 and 1. And if you can see that here, if we put any x here less than 1, like between -1 and 1, this puts a negative underneath the square root. So what we actually need, we need this to always be positive, even if x is positive or negative. So how we get around this, okay, so how we choose is by introducing an absolute value. Okay, instead of doing like, oh, choose the positive if x is positive, choose the negative if x is negative, we just throw in an absolute value. But that's basically what we're doing, okay? Because we need the choose positive when x is positive. Okay, and we need to choose the negative when x is negative. Well, guess what? That's the same thing as throwing in an absolute value. So it turns out at the end of the day that our derivative dy dx is equal to 1 over the absolute value of x times the square root of x squared minus 1. And that just takes care of the fact that this needs to be positive always. And that will actually finish and finalize our inverse trig derivative rules. Okay, and here we have the derivative rules completed. And just like before, if we do all this work again with cosecant, we just get the negative. We can just add those to the list. However, what I will say is the ones that you really need, we need the sine inverse, the tangent inverse, and the secant inverse. And honestly, when it comes to integration, it's these two that really show up. This one, not as much, but it's, you know, still good to know it and know where it comes from, why it's always positive. So these are the derivative rules. Now we can just map them back, right, to get the integral rules. So if we know it one way with derivative rules, we can map it back to get our integral rules. But there's a little bit more to it than just that. Now, I could just say, oh, since the derivative I'll use t, that's fine. The derivative of tan inverse t is 1 over 1 plus t squared. Since that's true, that means the integral, if we go backwards using the integral, that just means the integral of 1 over 1 plus t squared dt is tan inverse of t plus c. However, what ends up happening is this doesn't end up being as useful as we might like. In fact, what we're going to do instead is we want to generalize this a little bit. So we want to generalize the integral rules, because it turns out, based on what you saw in Cal 1, you might not believe this. It turns out that integration ends up being a lot trickier than differentiation is. You may believe that. I don't know. So anything we can do to give ourselves like way more tools, way more things to do is going to be helpful. So here's what we're actually going to do. We're going to look at this integral. I'm going to look at 1 over a squared plus x squared dx, okay, where a is a constant. Just any real number. So that means we could generalize this in all sorts of different ways, right? All sorts of useful ways. All right, now how we do this is then we try and get it to look like this, where we have a 1. We're going to try to get, that's an R, try to get a 1 here. All right, now thankfully I'm a mathematician and I can use algebra to get us there. Now what I'll say, if this is a little, you know, outside your pay grade, that's fine. Eventually we'll just have the rules and we'll use them, but for me it helps me remember them if I know where they're coming from. All right, so what I'm going to do, I'm going to factor out an a squared from the bottom, which may seem crazy because, yeah, there's an a squared there, but there's not one here. Now, how do you factor something out that isn't there? Well, you divide by it. Okay, because if we were to multiply this back through, we'd get a squared, and then these a squareds would cancel, and we'd get back right back to where we started. All right, so I'm going to do that. Then I'm going to rewrite this a little bit. Okay, I'm going to say that this is 1 over a squared, okay, times 1 over 1 plus. Now I'm going to rewrite this, since it's x squared over a squared, is x over a all squared dx. And now I'm going to use our good friend u substitution. I'm going to let u be x over a. Again, there are a lot of ways we could do this, but I'm just kind of doing it to I don't know, I wouldn't say easier way, but just this way. So if u is x over a, du is going to be 1 over a dx. Okay? Now I'm going to move that a over to get a du is equal to dx. Okay? So when I do my u substitution, I do my translation, this x over a will be my u, my dx is going to become a du. All right, let's give ourselves a little more room now. All right, so we get the integral of 1 over a squared all over 1 over, I think I said that wrong, times 1 over 1 plus, now this becomes u squared, and my dx becomes a du. And look at that, this a cancels with one of these down here. And now I'm going to factor this guy all the way out now that I don't need it. So I have 1 over a integral 1 over 1 plus u squared du. And now that is in the exact form I need it from up here. Right? It's good I use t's here because now we're going to use u's, right? So this ends up being that 1 over a transfers over, okay? And this just becomes tan inverse of u plus c. And now we put our x's back in, so we get 1 over a tan inverse of x over a plus c. And there we go. That is going to be the pattern that we set up our integral rules with. And remember, we just do this to make it more useful, okay? To make it more applicable in more settings. So we don't have to do this every single time we have some number here, okay? We wouldn't want to do that every single time. We do it once and we get the rule. Now, like before, basically just using the same idea, same work, doing the same stuff, going through the same process, we can get a similar pattern for sine inverse and a similar pattern for secant inverse. So here for sine inverse, we make it the integral of 1 over square root a squared minus x squared is equal to sine inverse of x over a. As we saw with the tan inverse before, the 1 over a squared plus x squared, that integral goes to 1 over a tan inverse x over a plus c. And with the secant one, again, we make it, instead of just x squared minus 1 in the denominator, we make it x squared minus a squared. Notice we don't put an absolute value here. Instead, it's moved over here. It's because we always, when we're introducing absolute values, it's usually as our answer, right? We introduce it. Now, if we were told that the x is positive, sometimes you're told that, then you don't have to worry about this. A lot of times that is the case. We're just told it's positive. I do want to mention, though, that these patterns, store these away for later. We're going to see this a lot. This a squared minus x squared, that is a sine pattern. Now, if it is stuck underneath a square root, underneath a fraction, then it is a sine inverse pattern specifically. A squared plus x squared, of course, that is a tangent pattern. Okay. Now, if it's underneath a fraction, then it's specifically tan inverse. Now, we'll talk about, when we get to it, what that actually means. And then if you ever see an x squared minus a squared, that is a secant pattern. Okay. Notice that we haven't done any patterns for like cosine inverse, cotangent inverse, cosecant inverse, and that is because we don't need to. All I would do is add negatives, and there's no real reason to do that, because you could do, if you had a negative here, you could just move it outside and just make this negative sine inverse, which ends up, being the cosine inverse anyway. I mean, the way it works out, okay? We just don't bother, honestly. In fact, the cosine inverse, cotangent inverse, cosecant inverse stuff, I don't tend to deal with that very often, even as a mathematician doing this stuff all the time. In fact, these two pop up a lot, okay, a whole lot. Now that we have our rules, let's go through some examples and just see how this works. Like before, u substitution will still hold, chain rule still holds for our derivatives, product rule, all of our rules still follow. We just have new rules to deal with. All right, before we get to examples, though, I do want to give you a quicker way to deal this with a chain rule. So if I have the derivative of sine inverse of stuff, right, usually, it'll be 1 over the square root of 1 minus the stuff squared times the derivative of the stuff. So I could put that here, or what I like to do is actually put it up here and just say, okay, it's the stuff, it's the derivative of the stuff over the square root of 1 minus the stuff squared. So tan inverse, oh, that was terrible. Let's try that again. Be u prime over 1 plus u squared And for secant inverse, it'd be the derivative of the stuff over the absolute value of the stuff times the square root of the stuff squared minus 1. Yeah, that secant one is the one that people tend to not like. And again, I'm only giving these because the cosine, cotangent, cosecant, and we just throw in a negative. Okay, these are really the important ones. All right, so from here, this will make some of our examples easier to do because we know that the derivative of the stuff is going to sit on top of the denominator every time. Okay, or sit in the numerator is what I guess I should say. All right, here we have y is equal to sine inverse of 5x squared. And we want to find the derivative. So dy dx, this is just going to be a chain rule. We have sine inverse of stuff. So it'll be the derivative of the stuff. So that will be 10x all over. And remember the pattern for sine inverse is, let me write it over here. If you write it every time, it'll be much easier to memorize. In fact, you probably won't even have to. It'll just sit in your brain. So it'll be derivative of the stuff, that's 10x, over 1 minus the stuff squared. So be careful here. This is all this stuff squared. Okay, we could just leave it like that, or if we wanted to simplify it, if we were feeling in a simplifying mood, remember we square everything, so it'll be minus 25x to the 4th. Okay, and there we go. Okay, we're ramping it up a bit. This one's going to be interesting. So we have y is equal to sine of 1 plus x squared times tan inverse of e to the 3x. Now, this really kind of drives home what you need to be careful about because this is a normal sine, not a sine inverse. Okay, and this is a tan inverse. Okay, so they will have different rules, and since we're multiplying, this is going to be a product rule, and since we have stuff on the inside of them all, it's going to be chain rules in here. Okay, so it may seem like all is lost, but we'll just take it a step at a time. Okay, product rule. So, two things multiplied together. We're going to start with product rule. So it'll be the derivative of the first. So I'm going to put that here in brackets. I like to keep things organized. So it is going to be, forget about what's in here. Okay. Usually I cover it up with my finger, but you can't see that. Just forget about what's on the inside. The derivative of the sine of stuff is cosine of that stuff, and we leave it alone. We don't touch it. Okay. Then we multiply by the derivative of the inside, and the derivative of the inside is, well, we have 1 plus x squared, so that will just be 2x. All right, and there's the derivative of the first guy. Then I'm going to multiply by the second guy left alone. That's our usual product rule, and we don't even mess with it. We just copy it down. Okay, then I'll put my plus down here. I don't know. Actually, I might have enough room if I shift things over a bit. So plus, now it will be the first guy left alone, so I'll just copy that down, sine of 1 plus x squared. Then it will be the derivative of the second guy. So now we're looking at the second guy. So now it's tan inverse. So tan inverse is, remember this u prime over 1 plus u squared. So it's the derivative of the stuff over 1 plus the stuff squared. So I'm going to put the derivative of the stuff on the top. Well, this is e to the stuff, and it's really just e to the 3x. So it'll just be 3e to the 3x. There's the derivative of the stuff, right? This is u prime. All over 1 plus the stuff squared. So I'll just copy the stuff down. That's e to the 3x, and I'll square it. Okay, so this here is our u squared. Right, now, with MyLabs Plus, should be able to plug this in all the way, just like this, and it probably won't fuss at you. But if you are trying to decide if it's like a multiple choice, it will give you the most simplified version. So you may want to simplify this a bit, clean it up a little bit. So let's say this is 2x cosine of 1 plus x squared times tan inverse of e to the 3x. Okay, plus, now, how are we going to simplify this? I think I'm going to make it one fraction. With simplification, there aren't really rules. They're just guidelines. Depends on what you're trying to do. Okay, and then here 1 plus. Now I'm going to square this. Now when you do this, when you take something to a power, raise it to a power, remember you multiply the exponent, so it'll be e to the 6x, and I'm going to say that's simple enough. Okay, so yeah, we really ramped it up there. Really stretched those Cal 1 muscles. Let's look at one with a secant. Okay, so here we have y equals secant inverse of ln x. Just a chain rule. I figure secant is complicated enough. So our derivative, so remember our secant rule is our u prime over the absolute value of the stuff times the square root of the stuff squared minus 1. So we're going to start with the derivative of the stuff. Well, our stuff is this natural log of x. So the derivative of this stuff is 1 over x. Already off to a good start, all right? Then be the absolute value of the stuff. So it'll be the absolute value of natural log of x times the square root of now the stuff squared. So it'll be the natural log of x squared minus 1. All right, and there we go. I think I'll just end it there. All right, and just to be safe, I'm going to just say that x is positive. Just to, you know, not worry about the whole, oh, actually, x does have to be positive because it's inside of ln here. All right, so x has to be positive, so I don't have to throw in an absolute value here, but that is something to worry about. All right, make sure you at least consider, because I know for sure MyLabs will fuss at you if you don't do it the way it wants and you don't consider these absolute value things. All right, so let's start looking at the integral examples. We'll start with a pretty simple one. Usually how I do this is when I see something like this, I first think, oh, this looks like a pattern I know. This is an a squared minus x squared underneath a square root, so that's going to be a sine inverse. Okay? Now remember, the thing to, and this does trip people up, the thing to remember is that this is an a squared, but our integral rule is an a. Okay? This is actually the integral of 1 over the square root of 4 squared minus x squared, and that makes our a 4. Okay? So then from here, we just fill out. Remember, when we go back to our, okay, so here's our rules. Sine inverse, notice, doesn't have a 1 over a out front. Okay, how I remember that is I just think sine is the nicest of the trig functions. That is objectively true. And since it's the nicest with its inverse guy, it doesn't have a 1 over a. Secant is the meanest of the trig functions. That is also objectively true. And that's why it adds in an absolute value. Okay, so sine inverse is the only one that doesn't. However, it does get it in its input. So when we go back to our problem here, our a is 4. This is a sine inverse pattern. Therefore, the integral is just sine inverse of x over 4 plus c. And there we go. That really is all there is to it. Okay, but it doesn't always give us something that nice, right? It's not always something that is a nice square of something else. Like in this case, if I have the integral of 1 over 5 plus x squared, well, when I look at this, I might want to explain why this can't be a u substitution. This can't be a u substitution because if we let u be 5 plus x squared, du would be 2x dx, and we don't have a 2x, or even we don't have an x up here, so this isn't possible. But it is our tan inverse pattern, right? It's the tan inverse pattern, but this is not nice like this one up here was. But you know, that's okay. If a squared is 5, a is just going to be the square root of 5. We ignore the plus or minus here, right? We just pick the positive when we do this. So there's our a. So now we have all the information we need to finish this off. This will be 1 over root 5 tan inverse of x over root 5. And don't ever forget your plus c. And there we go. Alright, some stuff to watch out for is when we start using these patterns in u substitution type things. So for example, if I looked at this and thought, okay, that's probably going to be a u substitution, and I let u be the entire denominator, thinking maybe that it would be like a 1 over u case, right? Our du, well, since it's e to the 2x, it'd be 2e to the 2x dx. Now, here's the thing. I have an e to the x up here, but I don't have an e to the 2x up there. So that's not going to work. So what you need to be on the lookout for is if you have something like, oh, a 1 plus something squared. Oh, maybe that's a 1 plus u squared, right? Maybe that's a terrible plus, but yeah, maybe I could rewrite that as a 1 plus u squared kind of thing. So let's try it here in yellow. Let's say e to the x over 1 plus, and I can rewrite this e to the 2x as e to the x squared. And now I'm going to make this the u. So u, I'm going to make e to the x, then du is e to the x dx, and oops, I see I messed something up there. I put a du, a little too early for that, I think. That's still a dx. Okay. Now, I have this e to the x dx. It's here. Okay? So that means I can replace this with a du, and this will be a u squared. So the new integral becomes the integral of, it will just be du over 1 plus u squared. And that is my tan inverse pattern. Right? That's just going to be, my a here is 1, so that makes it even easier. It's just going to be tan inverse of u plus c. Now I'm going to put my x's back in, so this will be tan inverse of e to the x plus c. Okay, so in my experience, that's where things start to get a little tricky, is when we start incorporating a u substitution with these patterns. But just be on the lookout for, especially in this section, obviously, but as we go down later, be on the lookout for these patterns. That's what I meant by, you know, store those ideas off to the side, because they will really come in handy. So for this next example, we see the integral of 2 over x square root of 4x squared minus 1. Now this is definitely just a secant pattern. Okay, I mean, hopefully that's pretty clear. The thing is, though, it's not just the x squared, it's a 4x squared. So there are two ways you can go about doing this. One is to use a u substitution, okay? Because what you would do is you would rewrite this as the integral of 2 over x times the square root, and then rewrite this as stuff squared. So 4x squared I could rewrite as 2x all squared minus 1. Okay. And then let u be 2x. Right? So that would give us a u squared minus 1 in our square root. The only thing is we don't have like a 2x here to match, but that we could deal with. Our du is going to be 2. You know what I forgot? I forgot my dx there. But so my du will be 2 dx, which is what we have. Okay. The only thing we would have to worry about, so here we could rewrite this as just du. Here we could write this as u squared minus 1. The problem is we can't just write this part as u because it's just x, but if we mess with this guy a little bit and say that u over 2 is equal to x, we could say that this is u over 2, and then mess with that a little more. We could take out that 1/2. Since we're dividing by a 1/2, we could bring it up to the top, and this would give us the integral of 2 times 1 over u square root of u squared minus 1 du. And now we can just integrate. This is just a secant inverse now. Right? So, and there's no a, so it's even better. It's 2 secant inverse of u plus c. And then we just need to make sure we put our x's back in. All right, and our u was, where was it? Here it is, 2x. Okay, so it'd be 2 secant inverse of 2x plus c. Okay, let me show you the other way you could do it. This is the u substitution way. Another way you could do it is just factor. Instead of doing a u substitution, instead just sort of factor out that 4. And I think most students will like this better, but if you factor out the 4, okay. I factor out the 4, just like we did earlier. Okay, I'll do it inside the square root for right now. When we factor out the 4 here, we'll be left with an x squared. And when we factor a 4 out of 1, well, remember we divide by it, just like we did before. And this is kind of messy, but we want to focus on this. The square root of 4 is 2. So we can take a 2 out of this and get in the denominator 2x, then the square root of x squared minus 1/4. And now it is a secant inverse pattern exactly, because here's our a squared. Right? We have x squared minus a squared, and these 2's cancel, and I'm left with a 1 up there, so gets rid of that too. If a squared is 1/4, that means a is 1/2. Remember our secant pattern. Let me rewrite this just a little bit so it's cleaner. So remember what our secant pattern does. It is 1 over a, so it'll be 1 over 1/2 secant inverse of x over our a, which is 1/2. And you know what I forgot to do last time? I need to make sure I do here. Absolute values. Totally missed that. Okay, I'm fixing it now though. All right, and when we divide by a fraction like that, this will be 2 secant inverse absolute value to x plus c. However, of course I just said that, and it turns out we don't actually need the absolute values. We're told that x is greater than 1/2, so x is always positive. So actually we can drop those. Or leave them. I mean, for me it's all the same. I think my labs will throw a fit, but there we go. I personally like this version better, but you can always just set up a use substitution, see where it leads. Okay, for this example, this one's really misleading, okay, because at first glance you might think, oh, here's my tan inverse pattern exactly. However, we have tan inverse here. So what we're going to do is, remember, this comes from the derivative of tan inverse. So I'm going to try use substitution. Now, remember, with use substitutions, there's not that many options. We could either do the denominator or we could do the numerator. If we did the denominator and let u equal x squared plus 1, du would be 2x dx, and we don't have anything like that. So that's out. So instead, let's do the numerator. Let's just let u be tan inverse. Then du, well, the derivative of tan inverse is 1 over 1 plus x squared dx, and we do have that. We don't see it, but there is a 1 sitting right here. So this altogether would be our du, and then this would just be our u. So believe it or not, this integral becomes u du. Like I said, this one was misleading because I made it look like we were going to do something, but it didn't turn out that way. This is just an integral of u, that's 1/2 u squared plus c. We have to be real careful how we write this. Our book uses this to the negative 1 power. I'm not a big fan of it. I kind of like to use, mainly it's because of stuff like this, because this would be tan inverse of x squared plus c. It's real tempting to make that to the negative 2. Don't do that. That's why I like this arctan notation. So I could just say it's arctan, which is the same thing, just it gets rid of the to the negative 1 power, which can be really confusing. So here at the end, our answer is just 1/2 arctan squared plus c. And there we go. For this particular example, your first thought might be, oh, that looks like a secant pattern, right? Because I have this thing outside, I've got this square root, but be real careful. Remember, the secant pattern is an x squared minus a squared. We don't have that here. We have the a squared minus x squared. That's a sine inverse pattern. Okay, so it's not going to be this one. It's going to be a sine inverse based on what I see here. But it does not look like an a squared minus x squared, right? Or if I wanted to be a little more careful, it doesn't look like an a squared minus a u squared. It just is 1 minus x. Well, if I say the u squared is x, right, that means u is going to be the square root of x, right? We could actually rewrite this problem as 1 over square root x square root 1 minus, and I could rewrite this x as the square root of x squared. Hopefully that comes across, that's a 2. Okay, there we go. Now that is this pattern. That's a sine inverse pattern. Okay, so we're going to let, I already have it written here, we're going to let u be square root of x. That's going to be our u substitution starter. then du, here's the trick, the derivative of the square root of x, that's 1 over 2 root x dx. Well, I forgot my dx here. Okay. Check that out. We almost have that. We're missing a 2. So let me bring that 2 over, and I'll have that 2 du is equal to 1 over square root x dx. And there we go. So I can make this u in here, and then this stuff I can make 2 du. Okay. So we'll get the integral. And keep this 1 up here as well. Like, put in an extra 1 if you need to. You know, maybe that's not in there, right? This is still a fraction. So we'll have 1 over, now it'll be the square root of 1 minus u squared, putting that new stuff here, 2 du. Okay, so I can move this around a little bit. So now this is just our sine inverse pattern. We'll have that 2 comes along for the ride. It'll be sine inverse of u plus c. Now our u was the square root of x, so we'll get 2 sine inverse the square root of x plus c. And there we go. All right, so hopefully that gets you rolling on the homeworks. And I'll talk to you next time.